Okay, welcome everyone for my talk about generative AI with Kotlin, LangChain, Spring AI. Well, I'm super excited. This is the first edition of Fox Days in Amsterdam. So I would really love to memorize that event with a little selfie, where it would be great to kind of reflect the feeling you have so far for the conference. So let's see, how do you like it so far? Yeah, that looks pretty good, pretty good. Oh, excellent. Cool, so let's hit the road. My name is Urs Peter. I'm a senior software engineer. Gray hair, right? Then you get the title senior. On my daily job, I try to be as much as possible with my hands in the dirt. I'm also a very passionate trainer, mostly about my favorite language, Kotlin, where I help teams in all stages of their Kotlin adoption, be it beginner, intermediate, or advanced. So who of you is using Kotlin? Ah, great to see. Excellent. Nice. And I'm also a frequent conference speaker. Enough about me, a little bit more about you, and especially about the usage of AI you apply. So who of you is using an AI assistant for coding? That's almost everyone. Okay, cool. So who of you has played around with an LLM? Also quite a few. Nice. Who has created an AI system that leverages these techniques? Okay, excellent, nice, cool to see, excellent. Well, if you had to describe our field of software development until some time ago, we could have said that it was more or less a predictable environment. A bit like a swimming pool, where we had more or less well-known aspects, like the one you see here, and I think most of the time we were enjoying what we were doing. Sometimes we had some issues with some parts of it, but overall we could say that it was more or less predictable. And then you had this big black abyss, right? And at the other side of the abyss, there were terms like the ones you see here, data science and so on. Some of us maybe crossed that line because they had to. There was a team where they had to work together with a data scientist, but overall we could say that these were really two distinct fields of expertise. Well, with the advent of AI, our peaceful swimming pool considerably got stirred up with a tsunami of buzzwords, new concepts and techniques, which, well, somehow demands of us that we have to take a stance towards it. I think this image nicely reflects the stage of AI we're in, right? I instructed the image generator to create an image that unloads a cargo in a swimming pool, and this is what you get. Nevertheless, as said, somehow we have to deal with this new area and the new possibilities, and as such, this talk aims to bring you AI closer within the cozy and well-known realm of the GVM, or Kotlin. By the way, this image I generated about half a year ago. Recently, OpenAI has released its new image generation capabilities, and I asked, hey, given this image, can you fix it, right? This truck needs to be turned around and made unload a cargo in a swimming pool, and this is what it came up with. So I think we still have some way to go till we are there. I'm not the only one having issues. There are quite a few projects by now. There are nice websites that keep track of all the failures of AI that have been created so far, which do not only result in failed projects, but really results in major claims and money that has to be paid to customers and so on. So it's a kind of a dangerous technology to put your hands on. And more on that also later. Well, if you're talking about AI, we're actually talking about these bad guys, right? The large language models. What are large language models based on? Well, they're neural networks, so-called transformer-based neural networks, which are good at processing data in sequence, and what makes them special is that they have this self-attention mechanism, which allows them to figure out what in the sequence it processes is relevant and what not. So it can kind of capture context of what it gets, and that context will then be used to do the processing. How they create it, you might have heard of that, I assume. They're created with tremendous amount of data. By now, OpenAI slurped the whole internet, so the question is, what's next? We're already talking about synthetic data they generate to still increase the models. And what you get then is models with a lot of these parameters. So what are parameters? Well, parameters are basically the weights and biases on the connections between the neurons. Well, it's a neural network, there are neurons, and there are connections between, and the biases and weights are part of that. That's not all. Also, parameters for self-attention and layer normalization are parts of these parameters. And, well, the rule of thumb is the larger the parameters, the better the model, kind of. Here are some examples. Mistral is a European model. There are not many European models, but that's one, made in France. Ships models with 7 till 140 billion. Why such a difference? Well, you also want these models maybe to run on an edge device, like a mobile phone or just a lower hardware device. So these are the models with lower parameters. And then you have the large models, which you run in a data center with the very expensive hardware, for which you probably have to call NVIDIA. Who has heard of DeepSeek? Almost everyone who follows the news a bit, right? That's kind of the China all of a sudden came around the corner with DeepSeek that was trained only with $8 million. In the end, it wasn't that, it was significantly more, but well, the damage was already done on the stock market. So their model has about 1 to 5 to 7 billion parameters, and then you have the latest GPT 4.5, which has 5 to 10 trillion parameters. And this is what you get, right? A GPT, generative, because it generates stuff, pre-trained, because it's trained with all the data, transformer, because it's based on the transformer architecture, GPT. What do LLMs do? Well, what they do is actually quite something basic. So they're really not intelligent. That's something we think should tell ourselves, even though it might look like it is, but it's not intelligent. What it does is, it simply predicts the next most likely token. So it's fully prediction-based. No intelligence, only predictions. These predictions sound pretty good because it's trained with so much data, you get pretty nice and decent text, but we also suffer from so-called hallucinations you definitely have heard of. There is a parameter where you can kind of adjust the degree of hallucinations, which is called temperature. So the lower the temperature, the more factual your reply will be. The higher, the more fictional it will be. And depends on use case. If you want to brainstorm, then maybe a more fictional response is nice. However, these hallucinations, they are kind of really breaking up the whole industry. So that's why by now we have seen different models arise, the so-called reasoning models. So OpenAI has these O1, O3 mini models. DeepSeek R1 is also a reasoning model. And Claude from Anthropic has a hybrid version even that kind of figures out by itself when to reason or when not. What is reasoning? Well, it's basically breaking down the prompt into a chain of thoughts, and by trial and error, they figured out if we do that, we get better responses. What's very important to realize is that LLMs are always limited to the data set to train with, right? So if your data set is incomplete, erroneous, biased, and so on, well, so will be the replies of your LLM. What are LLMs for us developers? Well, you can easily run LLM on your local machine. You have the so-called Ollama toolset, very simple to install, at least on a Mac, or also on Windows, I would say. Brew install Ollama, and then you just run one of those open source models. And that's what I've done here. So I use some films because sometimes network is an issue. Actually, this runs locally, but just for speed of it. A question I always have, which I never could find an answer, is how many letters are on the word strawberry, right? That's, I think, a very tricky question to ask. So that's a great answer, or a great question for a AI, artificial intelligence system, and it says it has 2 R's. Now I know. Thank you. Don't have to count. I count more, but apparently not. Because I count 3, I'm not so confident anymore. I maybe ask a reasoning model to do the same. So here I'm asking DeepSeek, which also can run with Ollama toolset. Let's see what it comes up. So you see there is quite a bit of reasoning going on. And well, I mean, I still want to talk about other things than this, so I'm going to speed this up a little. So there's quite a bit of reasoning going on. But you know, it doesn't matter if it reasons as long as the answer is correct. And I mean, at least it's consistent. I think there's a conspiracy between LLMs, and they agreed that strawberry only has 3 R's. And well, the point here is that if I ask this another time, then I get 3, another time I get 0. So what's really important to realize, and we also had this in the previous session, LLMs are unpredictable beasts. They do stuff that look like intelligent, but they're not, and as such, totally unreliable. We need to take that into account. Okay, If you want to send sensitive data to an LLM, you better deploy one in your own infrastructure, private cloud, for instance. That's what you can do. So you can send your whatever information to it. You also can use the public offering, but there, be aware of that your data might be used for training. So if you send a token there, it might end up somewhere in the training set, and well, you can imagine yourself what happens. However, if you take a step back, for us developers, an LLM is actually foremost this, just another API to interact with. A bit of special API, but nevertheless, just another API. And when we're talking APIs, well, then frameworks aren't far. The frameworks you can use to interact with LLMs on the GVM is LangChain4j, which is based on LangChain, which was initially created by Python, and which is already around for quite some time. So it's conceptually based on that, not in terms of source code. And it does all the things you see here. And when you walk out of this room, you should actually all know these terms and what they mean, what you can do with it. The other player is Spring AI, which in terms of features, it's really comparable to LangChain4j. Some have their strengths and weaknesses. At the end, I'm going to show you an overview, but yeah, it doesn't really matter which one you choose. They are more or less identical. Okay, so if we want to interact with an LLM, what do I have to do? Let's start out with some examples of LangChain4j. So that's what I've done here. If I just want to talk to an LM, then the only thing I have to do is using so-called chat language model, which I need to configure. By the way, that's something I should have mentioned. You see here a Spring Boot application, and I run LangChain4j in it. That's one of the features of LangChain4j. It's more or less a library that goes very well with all the major frameworks in the Java or GVM land, like Quarkus, Micronaut, Keytor for Kotlin. LangChain4j is compatible with these, whereas Spring AI is really dedicated for Spring. So if I'm using this Spring flavor of LangChain4j, then I just configure some stuff here, like my API key, the model I'm using, temperature, remember temperature, it's there. You have to configure it, and some other parameters, and then I can run it. So let's see what this would do if I call it. For this, I'm using a very cool feature, which is called a Kotlin notebook. So Kotlin notebook, I can just create some code, compile it, and then it's just present. So I just created this get method, and with that get method, I can now call my service, asking what is Fox Days Amsterdam, and well, ta-da, this is it. Who of you has used Kotlin notebooks? Only a few. Okay, that's definitely something to try out. Very cool feature to do very quick prototyping in a very convenient way. If you looked carefully, you've seen that the response was just appearing all at once, right? Tack, all of a sudden it was there. When you have length responses, that's probably not what you want. You want to get the responses more piece by piece, and for this we have to use a streaming approach, so to say. That's what you can use here with a streaming implementation. The way this works is that you would use such a streaming assistant, simply annotate it. You have to inject that. There is also such a chat language model that streams, but it's a bit more complex than the annotated approach. So let's see, there it is. And with that, I return now a flow or a flux, basically gives the Spring flavor of a reactive stream, which is a flux, which can convert to flow in Kotlin. And then the difference is quite evident. So instead of getting the answer all at once, I now get it nicely streamed. So my client can handle that. And now you see the response appearing. Peace mouth. Okay, let's take a look at what Spring Boot has to offer. As said, it's very similar to LangChain4j, except that it works with a client, right? The LangChain4j is more a bit this template approach we had prior in Spring. Spring nowadays advocates these so-called clients, where you can compose what this client needs to do. Here we say prompt, user stream content. Also here, guess what? We have configuration. So we need an open API key, the model we're going to use, the temperature. If I wanted to use my local model, I could enable these parameters here, just run my local model, local host, and then I could talk against the Mistral model. I'm using OpenAI because it supports cooler and a wider range of features. So what I, for instance, can do with Spring AI is the following. So I have here another prompt which wants or gives it the possibility to say, give me the most wanted dishes for a certain kitchen. Then you have here a interpolated argument. And instead of just replying with a string or just a piece of text, you can say, okay, I want the reply to be in a certain format. And as a format, I simply provide a data structure like this one you see here, dishes, just simply Kotlin data classes. And then what Spring actually does is it takes these data classes, it converts it to a JSON schema, sends this along to an LLM, so the LLM knows how to, in which format it needs to reply rather than just replying with a large chunk of text. This then looks more or less as follows. So I say here, Italian kitchen. And once executed, you see that now I get a nicely structured response. Can be very convenient, especially when you do, well, some checks where you then want to continue in a programmed way rather than just with text by itself. Okay, last but not least, what Spring AI is also pretty good with is so-called media queries. So that's what we have here. What you also can send to at least OpenAI, local models like Mistral do not support it, but OpenAI does support that. So you send a URL or an image, and then you can ask questions about that image. So detect all the objects on that image. And this then would look as follows. So here I have a URL of some image. Again, Kotlin notebooks, cool that you can print some HTML, so you can put anything HTML can output, you can put in there. I execute this call, and now, again, in a streaming fashion, I would get the contents of that image delivered. So quite cool and nice feature, especially for a demo. However, well, even though this is kind of cool, what does this deliver you for business purposes? It's just kind of a programmatic way to talk to an LM. All the tools these cloud providers or these LM providers offer you are probably better than if you write it yourself. So the added value might be quite limited. I was wondering, this problem has miserably failed. McDonald's has created this order system that allowed to order things with McDonald's by voice, and it quite failed. There were people that got about 1,000 hamburgers delivered, things like that. So eventually they decided to shut it down. It was created by IBM that started the project in 2019, and in 2019 we didn't have all the capabilities like the ones we have now. So let's see if we can maybe rewrite this whole thing in a better way, applying new techniques. And along the way, I will actually also show you more details what these techniques all imply. And of course, you're not going to do fast food. You know, fast food is so out, so we're going to do something delicious. We're going to create this guy, Italian Delight, the AI-powered Italian restaurant. And what do we want to accomplish with that? We want to actually accomplish two things. First of all, we wanted to kind of know about our menu. It's kind of handy, right? If you can instruct LM to use the data I provide and not its own data it's trained with. And second, also want this ordering system to execute some code on my side, execute an order. Which brings to our first problem. How do I provide my own data to this LM? What kind of options do I have there? There are actually two. The first one is so-called fine-tuning. So you take an existing LM and then you, in kind of specific language, you would kind of freeze the weights. That's what it's actually done. So you have all these layers. You would freeze many of them. You would keep some output layers open, then would retrain this model with your own data. And with that, you get a so-called fine-tuned LM, which would contain our menu. Well, there are quite some disadvantages with this approach. So first of all, it's quite costly. Retraining models is not cheap. And second, at the moment, my menu would change, which definitely would be almost daily, because I also have some sort of daily menu, it would already be outdated. So this approach only works for specialized LLMs. For instance, healthcare, or maybe the code assistants you're using, they're also using fine-tuned LLMs. So the approach we probably have to do is this one, retrieval-augmented generation, RAG. Probably have heard this term. I always found it a bit of a weird term, even though when you even look at the terms, it makes sense. So how does that work? Conceptually, it's not hard. It's quite easy the way this works. So you get a prompt, and with that prompt, I'm going to look up data that is similar to the prompt. Well, that's the so-called retrieval step. I retrieve data that kind of enriches the context of my prompt. Then I send this prompt along with the data I have retrieved, which is called augmented, right? So the initial data is augmented with the data I've retrieved. And then the LM would do the generation, would do whatever is needed to do with that particular data. Now you might ask, why all the hassle? Why not just send the whole menu all the time along? I mean, that's something we could do too. Then we kind of would avoid the retrieval step, would be considerably easier. We can do that, but there are some considerations. So first of all, this would be a bit more costly because a menu can be quite long, and each request you would have to go through that whole menu, which costs you tokens, and also a bit of processing time. So that's a disadvantage. And what you also get is that because you just throw a lot of information at LM, the reasoning might also suffer from it. So an LM is already unpredictable, but if you want to make it even more unpredictable, that's probably a good approach, just to send it as much data and then hope that it will figure out the right one. So it's kind of valuable to limit the amount of data to the context you provide. That's why we want to jump through that hoop. There's, by the way, another term which I like much better, which is called stuffing the prompt. I think that makes sense, right? This sounds very simple, but it's actually quite advanced. So somehow we need to ingest data in some data store so that it can be found with a prompt, right? That's a different magnitude than do a SQL-like query. That's really a different order of complexity. And in order to understand how this works, we need to take a step back and look at this practice here, NLP, natural language processing. Natural language processing is the field where computers understand and generate human language. And with that, we can do things like that, semantic search or similarity search. So, for instance, if I search for the word king, I also expect a value spec that are related to king, like monarch, prince, emperor. Even though, from a syntactic point of view, they have nothing in common. The cool thing is this also applies for whole sentences. I think you might be like, this guy scratching head, how is this accomplished? How can I, when I look for king, get words back for monarch? How do they do that? Well, it's actually not that hard, the way it's done. The way it's done is that you assign meaning to words by means of a so-called n-dimensional vector. That's a very fancy word, but it's actually just an array of numbers. So what we see here is the dimensions of the vector. Generally, it's about between 300 and 2000. And every dimension, so basically the index position of that array, represents a certain characteristic. So index position 0 would be royalty, the next masculinity, femininity, and so on. And then for every word, we can fill in every dimension, and so to say, set the weights. And by doing so, we now get a pretty good idea what this word actually means. How are those weights defined? You're probably not going to type them all in yourself. Well, for this you use training. And the basis for training will be a large so-called corpus of text. So you just take a tremendous amount of text, and within the text, all these dimensions should automatically emerge, right? So when you use a book about knights, probably the word with king and castle and so on would kind of relate to each other. And as such, it is very important that your corpus is really representative. If you take a corpus that is not large enough or that is specialized or too generic, then of course you won't capture the right meaning of a word. So that's very important to keep in mind. Once you've actually assigned meaning to every word, then you're not talking about a vector anymore, you're talking about an embedding. That's also a term which you will very frequently hear. Under the hood, it's slightly different. We're actually not vectorizing words, but tokens. And you probably also have heard the word token. You paper token, right, in LM. So what the heck is a token? Well, when you have such an embedding model, it actually has two parts. It also has a tokenizer. And tokenizer is splitting up words. Why is it doing that? Well, for these reasons, as you see here, it reduces vocabulary, and as such also better captures semantics, which then ensures faster processing. So now we have tokenized our input. Then we're going to map every token to an ID. And then for every ID in this embedding model, we can look up its corresponding vector. So the word de is mapped to number 12, and number 12 has then these vector assigned. Now the cool thing is that this also works for whole sentences. How does this function? Well, imagine we have this sentence here: the queen rules the kingdom. It is composed out of all these different tokens. And now we just can put some math at it, so-called aggregation algorithm, that takes all the individual vectors and aggregates them into one. So the final result, as you can see here, scores on masculinity and femininity about 50-50, because there are still masculine and feminine words in that sentence. And as such, we can capture the meaning of a sentence, again, by a single vector. It's quite nice that we can play around with that. So LangChain4j has quite a few tools where you just can very easily demonstrate how this works. So here I'm using this particular embedding model, just an existing model, open source one you can use. There are a variety, and you really have to look at how they're trained and what kind of capabilities they have. So here I create an embedding for the word kingdom. That's one also we've seen. And let's figure out how many dimensions this kingdom vector would have. And you see that it has 512 dimensions. And believe me, there is really a vector behind it. This is the vector representation. And if you look at the size, then you see that, yeah, indeed, it's 512. That's the dimensions of the vector. We also can look at the token usage, so how many tokens were used to create that vector. And we see it's indeed 2. So in this particular embedding model, tokenizer chose to split the word kingdom into 2 tokens. So why is that so tremendously important? Well, because now we have numbers, we can feed them to computers, because computers can handle numbers very well. And that's actually our next step. What we want to know next is how similar are words from one another. So in other words, how similar are vectors from one another. For this, you have this fancy term, cosine similarity. That's just a mathematical formula. I showed it here because that always looks impressive, right? Formulas. And there are more you can choose from. This is the one you probably hear most. That's what I'm doing here, creating some extension method, cosine similarity between. And now I can check how similar is the word king to the word cat. There's not a lot of similarity. Probably queen would make it a bit more similar, right? So king and queen are more similar. So one would be similar and everything below less similar. As said, also applies for all sentences. So the king is in the capital, kind of similar. But if I said Kotlin rules, so let's see if that's not really similar. Even so, ruling I would have expected to a certain degree similar, but well, the word Kotlin itself has nothing to do with king, so similarity is very low. Okay, so that's kind of nice and dandy, some math and some vectorization. How do you integrate those techniques in your own application? How do you do that? And this is actually the next part we will tackle. So we would take our menu, then we would create some essential parts of our menu, kind of produce a string out of it, like the menu name and maybe some ingredients, and this we would vectorize. Once you have such a vector, we want to store it somewhere in a vector database. More on that in a minute. Once we've done that, so we have a vector now and the corresponding string, we can do the same with the prompt. So we also take the prompt, we vectorize the prompt, and then we have actually vector against vector, math against math, and as such can create such a similarity query. And then I would get the text back that corresponds to the most similar vectors. So we need to talk a little bit more about vector databases. Well, guess what? They're databases that can store vectors. Haha. Vectors are actually a very powerful capability, which is not really, has actually not much to do with LLMs. It's actually a new separate field that allows you to do all these things you see here. And the way this is done is by applying so-called k-nearest neighbor algorithm. So imagine if I have all these vectors, so these would be very simple vectors with 2 dimensions. That's why I can show you in a 2-dimensional space. Imagine I have a query which would kind of have a vector of what you see here. Then I could say, give me the nearest neighbors in a certain radius. That's k-nearest neighbor algorithm. That's kind of nice, but imagine if you now have 100,000 vectors in a database and you come with another vector and say, give me the nearest, then it would have to process all those vectors in the database. So that would take you really a long time. So it's computational, very, very expensive. And that's why vector databases came with the solution of a specialized index. These are some of these indexes. They have very fancy names. What they do more or less is this. So instead of k nearest neighbor, they do approximate nearest neighbors. And this works as follows. So whenever I insert something in a vector database, it will be assigned to a cluster. So every vector will be part of a cluster. These are the big colored elements you see there. And then when I do a query, I would also assign the query to the cluster. So the vector the query represents will be then checked to which cluster it belongs. And then I would take the approximate nearest neighbors, which would lead to the, possibility that I would miss certain items. So here I trade basically performance versus accuracy with approximate nearest neighbors. And as such, it's fast, but yeah, not that accurate. There are a lot of vector databases out there. The cool news is for us developers, at least GBM developers, Postgres has an excellent vector extension. So you just can use your well-known, familiar Postgres database. And this is what we're going to do next. Again, with LangChain, so LangChain4j has these tools. Spring AI has more or less the same, just in different shape, but they can do really more or less the same. In Kotlin notebooks, you have a very convenient feature which is called data frame. And a data frame allows you to very easily to explore data. So I'm just loading my menu, which is in CSV format. I say generate code head, and then it shows me how this CSV is looking like. What I then need to do next is convert my CSV to a so-called document, and this is the one that will be vectorized. And the most important part of this document is basically this. This is the content that I want to vectorize. So I'm going to execute this, and then you see actually what this content is getting. So I'm just printing this here. So this is the content I'm creating, the dish name, the ingredients, and this is what I'm going to vectorize, hoping that this will be enough to get good matches for my prompts. Getting the data that you want to vectorize right is an art by itself. So there are really tremendous amount of approaches that allow you to vectorize your data in a way that you always will capture the right essence. It's quite a complex topic, and the final solution is not there. It really depends on your problem. Okay, then I'm going to embed this whole thing. So for this, I need an embedding store. I need an embedding model. And the only thing I need to do now is feeding my documents to that ingester. So now it will vectorize the sentences or the strings I've created and store it in the database. With that, I can do the cool stuff. I can do similarity search. Also a nice feature of data frame, I also can talk to databases. If it's a CSV file database, it's just a data source and it can handle that. So this is the result we have accomplished so far. So I have here my text, the one I've created, and this would be the corresponding vector. And with that, we come to the final, the culprit is that I take now a prompt, I vectorize it, simply create an embedding of it like we did before. And then I simply can do a SQL query with a special operator. It's basically this one here. This is the operator. Instead of a like query, this is a call sign similarity query. And then it would apply this approximate nearest neighbor search capability and then retrieve me the most similar vectors with a certain score, right? So my score is now 0.7. So if they have this similarity, then it should be in the result set. If I increase the score, then of course it will be less. That's basically it. Creating text to numbers, and from there on use simply pure math to figure out what is similar, which data is similar and which is not. With that, we now can create our chat application. And before we're going to create the chat application and do the interaction with the LM, we need to know a little bit more about a prompt. So how does actually a prompt look like? prompt is quite a structured piece of data. It's not what you might think that you just enter text and this is what's going to be sent to an LLM. No, it's a structured data format. The most important role we have here is system. This is actually the message that defines how a LLM needs to behave. This is where you set the certain preconditions, even some certain guardrails you can build in there, even so the other approaches. It's just actually the idea how the conversation needs to be conducted. Then you have the so-called user section, in which you would put the prompt the user put in, alongside with the context you maybe looked up in RAG of iRAG. Then you have tools, more on these later. Then you get a reply from LM, and the LM replies in the assistant role. And as such, actually the whole communication between input, output, LM is captured. When you have a conversation, it kind of helps to keep track of what is said before, because an LM is fully stateless, so it doesn't store any information. So when you want to have some data that refers to an earlier part in the conversation, you always have to send it along. And this is basically what you have to do here. You have to also provide some chat history, which is simply actually all these different snippets accumulated to a certain degree. And the latest entry in the chat history normally is the latest message. So the LM would consider this one or assign the highest priority to this piece of data. Okay, so let's do that. We do this in Spring AI, right? So just to see that you can nicely mix and match the two. So this is how our chat would look like. So I have here a vector store, which is injected. That's what you see here. Just have a vector store, which you can nicely configure here. So I configured Postgres. I'm using this cosine distance to do the similarity check. And maybe remember this HNSW. This is the index we are using. So all these terms kind of also come back in the configuration. This can be injected, and then it's quite simple. So I have my prompt here, which has some message, and then I simply say message similarity search, give me similar documents. That's what I get back. And then I feed those documents to my prompt. I also define a system prompt here. That's my system prompt that gives the boundaries for my conversation. It says, hey, you're a waiter. Your chapter is to help. Customers do some ordering. This is how you start, and so on and so on. And also telling that consider the context under this context. So this is the prompt user query. This is the prompt. And when your prompt will be about food, consider the context. Otherwise, leave it out. Now we don't have yet the history involved. You also want to have the possibility to handle the history of our conversation. And for this, you simply can add a so-called advisor, where you need to assign some conversation key, a bit like a session ID, which then will do a lookup. It's like a map, right? It would look it up either in memory or in a database. Up to you. In a serious application, you definitely would use a database, but for these purposes, in memory is good enough. And then it says, I will keep 50 entries of my history. That's more or less how it works. And with that, we can actually talk with our system. That's what we do here. So I created a very simple client. That's what you see here. Say hi. Then the agent talks to my OpenAPI LM API. Here say I want a dish with pasta. So I would do the RAG lookup, would add it to the prompt, and then the LM kind of fabricates a decent reply, saying, okay, these are the options that fit your preferences. That's more or less it. Okay, so far so good, but with that I can do a selection, but I cannot yet order. I also want to be able to order stuff. How can I accomplish that? And with that we need to look at the LLM agents. You might have heard of that, Agentic AI. There are even kind of okay, let's first take a look at what Agentic AIs, what LM agents or Agentic AI actually implies. If you know the area of BPMS, Business Process Management Systems, which were popular 10 years ago, that's more or less it, but then on steroids. And because we know that LMs are fully unpredictable, it might also turn out like this, right? BPMS on drugs, because maybe most of the time it behaves well, but not always. So how does it work conceptually? Whenever I get a prompt, then alongside the prompt, I also send a variety of tools this LM could invoke if this LM think, now it's time to do that. And how does the LM decide to invoke which tool? Well, you send a description alongside the tool. I said tool number 1 is the function to order dish. Tool number 2 is to give information about, and so on. And then with the elaborate reasoning of the LM, it can decide, okay, now I think it's time to call tool number 1. And that's what it will do in its reply. It say, okay, you should now execute tool number 1. So LM will never execute anything. Of course, you don't want OpenAI to call your APIs. It just tells you, now it's time on your side to invoke that particular method. It even provides you with the parameters. And then you would execute this particular tool, which really can be anything you can execute, right? This can be an API, a web search, a database lookup, something in a file system. The sky is the limit, and as is the danger associated with it. The reply you also would feed back to the LM. So if you have a meaningful reply, the LM can even do something with the reply. That's what we also will do in a minute. The call might also fail, and LM can again reason in a different direction. This is actually how you're able to invoke LM stuff on your side. That's the way it works. Okay, let's build that in. Again, with Spring AI, it's a piece of cake to do that. What I have to define is a function. It's a simple function with some input and some output. It's fully Kotlin compatible, as you can see. You just use some data classes and it just works. That wasn't the case until recently, so they now made it fully Kotlin compliant. And in my particular function, I simply do some logging, but in a real scenario, you would, of course, do some database lookup, call a remote API, whatever. Here's my order response, and what I reply is that when you can expect the meal to be delivered. So delivery in minutes will be the reply, and we hopefully also will see that LM will make use of that. Then I just register this tool callback. This is how I register it. The only thing I need to do further is actually two things. I need to register that tool here in my conversation. So I say tools, I say order service, and I also need to instruct in my prompt, or I need to add an instruction in my prompt to say, okay, when you've reached that particular stage, execute that tool. That's also something I could send in the definition of the tool, but well, this is kind of the creative way how you make the beast behave in a way that it does what you want. And there are really different ways of possibilities. So it's far from engineering. It's actually way more trial and error engineering. That's what working with LMs most of the time is. So let's do that. So here I have my order section of my system prompt saying, okay, when the client has chosen a meal, then you have to trigger the order service and also reply with the minutes or the time that is returned by this particular service, or the time indication. Okay, and then we're actually ready to go to have even some code executed on our side. So we do the same here. We select the dish. And now we say, okay, I choose this particular one. And then it says, thank you for your order. You've chosen seafood paella. That's what also chosen, number 3. And when we look now in history, we see that this particular piece of code has been executed. If you look a little bit deeper, I think it's kind of nice to demystify it, what's happening under the hood. So this is the response we get, and in this response you see certain choices that are returned, which part of that is tool callbacks, which says, hey, you have to call the order service with this argument. So, and as such, it can populate my request object. Then it will be executed, and in the reply we get the delivered in minutes, which also was part of the text then the LM replied. So input and output can then be used for the LM to produce a nice answer. Okay, last but not least, nowadays we live in an age where we are talking to computers, so how can you include text-to-speech or speech-to-text? Also, that is really a piece of cake. Surprisingly simple. You have so-called speech models you would inject. I'm now only actually using text-to-speech and speech-to-text. It's something I can maybe do later. I'm using the exact same logic here above, but I convert simply what I get returned here into speech. That's it. And with that, we get more or less the final version of our application, which should talk.
Welcome to Italian Delight. How can I help you today?
And I think it's time for dessert because we already had the main dish. So let's see how the dessert
Based on
looks
your
like.
preferences for a dessert with cream, biscuits, and a coffee taste, I recommend the tiramisu. Would you like to order this delightful dessert?
Well, I think not bad.
Thank you for your order. You've ordered tiramisu. It will be delivered in approximately 20 minutes. Enjoy your dessert.
And with that, we more or less created alpha version of our ordering system, which definitely is not production ready yet because there are no guardrails. So depending on how I manipulate prompt, you sometimes get back really weird stuff. So making this reproduction ready is totally different attitude, but the basis for a nice demo is definitely given. So little wrap up about LangChain4j versus Spring AI. So which one would use? I would say the power of LangChain4j is that it's very modular and customizable without too much Spring magic. So you just have nice building blocks and you can easily orchestrate them. Whereas Spring AI is just the familiar Spring AI convention of configuration approach, right? It just works. Maybe sometimes you get very weird errors, but then you could do a configuration, it would more or less do what you want. But for more customization, LangChain4j does a great job. LangChain4j works with a variety of frameworks. That's what you see here. The only problem is that Spring Boot, of course, is the most used framework. 90% of the market uses Spring Boot. Then you have the rest, so to say. So that's why I think Spring AI will still capture quite a market share. LangChain4j, so in terms of features, what I found is that it has some interesting concepts to do so-called RAG routing. So now we just had one RAG source, right, the menu, but maybe you have multiple RAG sources. And then you need to do some routing. Otherwise, you cannot just ask all these sources to integrate all the context. So there are some strategies. You also can, again, do this with an LLM. Say, LLM, classify my prompt, which RAG do I need to call, and use a tool for that. So there are very different ways how you can get to the same result. But this has, again, advantages and downsides, probably will take longer, and so on and so on. Whereas Spring AI, as an addition, has also good transcription support. This is something which is not there yet in LangChain4j. And also the multimodal support is better in Spring AI. What I really like in LangChain4j is that they have a lot of tests with a variety of samples. So if you want to get more familiar with these concepts, just look a bit, scan through the tests, and you get quite quickly a good idea how you interact with this new kind of universe. Whereas the Spring AI documentation is just, well, as Spring in general, decent, understandable, well done documentation. Okay, and with that, I hope that with the knowledge you gained so far, you will face the future with AI, hopefully with confidence, enjoying a slice of pizza you just ordered with our newly created Italian Delight restaurant, and, well, maybe, hopefully, leave this room as a AI row. Thank you. Yeah, I think in terms of questions, because we have 40 seconds left, I would say we take them here at the table if there are some. Thanks for joining.